Hello, everyone, and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is Relay Test Management Software Training Advanced. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you will see a control panel that looks similar to this one. There we go. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during our Q&A segment at the end of the webinar. Additionally, the certificate of attendance, copy of the presentation, and a link to the recording of this webinar will be sent to all attendees in 2 business days. Our presenter today is Abel Gonzalez, Applications Engineer. Also, to assist with the question and answer session, we will have joining us David Beard, Relay Applications Engineer, and Sugosh Kuber, Relay Applications Engineer. All right, well, let's go ahead and get started. Thank you for joining us today, Abel.
Thanks, Mike. I just want confirmation. Can you hear me well?
Yes, we can hear you great.
Okay, thanks, Mike. So, like Mike said, today the goal of the presentation is to go over some of the, let's say, advanced features of our relay test management software. We have had quite a few presentations over the last few months where we've gone through a lot of the features of the software. Namely, Sugosh did a very good presentation on the on some of the features of the software, a basic introduction to it. And David, I believe it was last week or 2 weeks ago, he did a very good presentation also on some of the testing that you can do with the instruments and with the relay test management software, Rtms. Now, Rtms is a part of PowerDB. So to get to Rtms, you will need to install PowerDB and open it. So I just want to go over a few of the basics that you need to understand or know in order to get to the more, I would say, advanced stuff that I would like to cover. As part of PowerDB and being the relay test management software, in order to open the Rtms, we would go to the SMRT type units, and we would decide how we want to connect to our instrument. If we're going to use Ethernet, we select so here. We can ask the software to auto-discover the unit, which means that the software can find the unit that's connected to the same network that the computer where the software resides is in, or we can type the IP address of the unit in case we know it. If we are not using the Ethernet to connect to the unit, we will use something else. We can use serial port. Remember that the SMRT units, you can use USB or Bluetooth to connect to those units. In this case, we are going to use Ethernet. We're going to leave the software to figure out what the IP address of the unit is. And in this case, I have a unit connected to my computer. It's an SMRT 410D, which, as you can see here, has been connected for quite a while, 317 minutes since the last time the unit was turned off. It has been connected continuously all that time. On this same button, when the software finds a unit, you will see the serial number of the unit and the IP address of that unit that's connected to the software. I am going to select the connection to the unit right now, and I am connected to the unit at this time. Now, I want to go over some of the, let's say, very basic but very important things that I want you guys to remember before going into the more advanced stuff. Now, protection testing 101 consists of injecting magnitudes into the relay, sensing the response of the relay in an input of the test set, and timing or reporting the results of those actions that were, done by the things that were done by the relay. In this case, let's say that I want to inject a pre-fault of 500 milliamps for a period of, let's say, 2 seconds, just so you guys can see it, and that I want to, after those 500 milliamps for 2 seconds being injected into the relay, I want to inject a fault of, let's say, 15 amps into the relay. Okay. Now, where do I want to sense that the result or the trip of the relay? I want to sense it on binary input number 1. Remember that the configuration of the binary inputs is right here. Now, in this case, I am going to configure the binary input as a dry contact. If I wanted to use a wet contact, I would select so here, but I'm going to select it as a dry contact, and the input action is going to be operate on close, meaning that I am connected to a normally open contact that is going to close when an operation is sent out by the relay. Now, in this case, I am telling the unit, my SMRT, to use this binary input number 1 as the trip and to latch once it senses the operation the first time. I'm going to also allow some debounce time of 2 milliseconds, and I'm ordering the unit to turn voltages and currents as soon as it receives the trip from the relay. Okay. So again, what I'm doing is I'm injecting a pre-fault, then I'm going into a fault, and I'm sensing the operation of the relay on binary input number 1. Now, this may sound, I don't know, too simple for those of you out there, but bear with me here. This is very important, and it's very important that you guys remember this when we're going forward with the presentation. Now, I have a relay connected only on phase A at this time to my unit, and what I'm going to do is I'm going to play the test. Now, remember the difference between this button here and these 3 buttons here. This one simply injects the current or the set of voltages or the system of voltages and currents that I have selected here into the unit, but it doesn't time how long it took for the relay to trip. If I want to do timing, if I want to actually calculate or determine the time of operation of the relay, I need to use this button here. This is what I'm going to do right now. I'm going to run this pre-fault and fault test. When I run it, I will see that for 2 seconds, I have 500 milliamps, and after that, 15 amps were injected into the relay, and we got a trip time of 423 milliseconds. Now, what's going to happen is I'm going to add these results to the report. And as you can see here, we have a report that's made of the pre-fault time, all the operational characteristics, all the things that happened during the test. We had a pre-fault, remember, of 500 milliamps. We have a fault of 15 amps. The pre-fault time was 2 seconds. The operation measured time was 423 millisecond. And remember that I can now tell the software what were my, let's say, minimum and maximum expected values here, so that the software can evaluate for me whether the test passed or failed. In this case, I'm going to, because I don't know exactly what the relay settings are at this point, I'm going to say that the minimum should have been 0.4 and the maximum should have been 0.5. In this case, I'm getting a pass. And again, this is the basic thing that you do with the RTMS. You inject currents and voltages into the relay, and you get a trip time. And you evaluate whether that trip time was correct or not, depending on the settings that you have on the relay. Now, don't discount this, because this, I would say, is the way to test everything when it comes to protections Of course, the tools that we have allow you to do this kind of testing easier for you, but what our tools do essentially is use this same concept. They inject magnitudes into the relay and sense the outputs of the relay and then evaluate the tripping or not tripping of the relay, depending on the conditions and the settings that the relay had. Now, as we have been doing this, we created this test. A test module has been built for us. Now, see how this test is now, the timing test is now part of a group of tests, and it exists here, and it's added to the the group of tests that that we have on RTMS, and it's added automatically as soon as we add those tests to the report. We can from here execute that same test again. We can do so pretty easily simply by selecting the test, and we have just run the test one more time. We could have done it from here. Wherever you see this button on RTMS, it means that you can run the test from there. We can here, if we want, we can change the name of the test. I know that I am connected to phase A on the relay, and I can say that this is a phase A timing. And if I know the element that I'm testing, I can even say, hey, this is phase A timing for a 51 or for a 50, or let me guess that it was a 51. I don't know exactly. We'll get into that later. Now, I wanted to run everyone through this basics because this is, again, the basic for every test of protection systems that you have out there. Injecting, sensing, evaluating, and reporting. And our report, the actual report, is being built as we do the different tests, and it's being built with the tests that we add to the report. Now, in the report, we can add all the information that we want. Where was it that where was that relay that we just tested? Substation could be on my desk. The position it could be on top shelf 1. The equipment location at home. Test status was a pass. Why was it a pass? Because all the tests that we have in this test sheet were passed, and this is done automatically by the RTMS system for you. Now, I am going to go back home, last screen. This is a simple test that we just created for you. Now, I want to do a, let's say, and now that was an overcurrent test, and I can do all my overcurrent tests from here. But we have a tool that over which both David and Sugoj already went, but I want to show you something that you can do with our overcurrent timing tool. Let's say I have a relay where I have the following. I have a phase overcurrent with 2 elements. Now remember, this is the 50 element of this relay that I have right here. And in this relay, I have a maximum phase overcurrent of 15 amps with a delay of 100 milliseconds. And I have a second maximum phase overcurrent of 27 amps with a delay of 0 seconds. This is what you would call a high and low setting on the instantaneous. But on top of that, on this relay, I have a maximum phase time overcurrent with a characteristic of a pickup of 4 amps and a C1 curve 0.08 time dial. So here I have 3 elements, and I want to test the 3 of them. Now, one way of testing it would be designing 3 different tests, just like the one that we did. And we could go that way. We could test, I don't know, like 7, 8 different tests, but we can do that. All of it, we can test in the same sheet right here on RTMS. Okay. Now, in this case, I only want to do the timing test. I don't want to go over pickup and instantaneous pickup tests because that's something that was already done by both Sugosh and David at some point. My goal here is to show you that you can actually test all of the elements in the same sheet. Now, I am not going to use phase compensation. I'm not going to apply any pre-fault before the test, but I know that the pickup of my phase time over current is 4. I have a C1 curve, and I have 0.08 as my time dial. So it was a C1 curve. It's a 4 amp pickup and 0.08 time dial. Now, my instantaneous, for those who have very good memory, are going to be at 15 and 27. Okay, so now I have my instantaneous at 15 with a delay of 100 milliseconds and my second instantaneous at 27. And when I go to my timing characteristic, I can see that my curve and both my 50 elements are there together, all of them, and I can test them in one single test. The only thing I need in this case is to add a test point that is able to evaluate the last of the instantaneous elements that I have right here. So for that, I know that my instantaneous was what? 27 amps. Well, what I need to do is add something like 32. Okay, now remember that the maximum current that you can get out of the SMRT channels, and I am using a current channel, the yellow channels, for those who remember how the SMRT units look when you look at them. The SMRT is capable of giving me 32 amps continuously, or up to 60 amps for up to 1.5 seconds. Now, the trip time expected for this last element is, remember, that it is an instantaneous or an element with no intentional time delay, and I am allowing for up to 50 milliseconds of error. Now, I know that this relay will trip below the 30 millisecond mark or something in that area. So I can actually increase the amount of current that I want to inject to something higher than the maximum continuous capability of the current channel. As long as I'm not injecting more than 60 amps, I should be good. So what I can do now is I can run the test. But before that, remember, we are going to inject current, but we haven't selected which binary input we want to use. So I am going to select binary input number 1, and I'm going to run the test. Now, when I run the test, you'll see what happens. And this is a real test. I'm running it live for you here. The relay is actually tripping. So see how I injected 8, 12, 20, 45, and I tested all of the times for this element in a single test. And on top of that, this went into the report, okay? And a test was added to my test module with the overcurrent timing for that particular relay that I have right there. Now, I could have added more things here to the overcurrent test that I just created. I'm trying to keep this simple so that I can show you the nuts and crannies of what comes next. But I wanted to somehow summarize what we have done so far. What I did is, and you guys will probably see this type of characteristic in a lot of overcurrent relays out there. Now, overcurrent relays are the most common type of relay. I have been to substations where I could say that 99% of the relays that were in the substation were overcurrent. And sometimes it's overwhelming, the amount of overcurrent relays that and elements that you have to test in a single substation. So having a tool like this, do something like this, is very useful. And you have some relays that have a composite characteristic that looks exactly like the one that I'm showing you here, where you have the 51 the low set and the high set instantaneous all in one, and you can test them all in the same, let's say, screen with RTMS. Now, what I want to get into now is what happens if my relay settings change, and I am testing, and I want to, be aware of those changes, and I don't want to have to change the tests myself. I want the software to be aware of those changes on the relay settings, and I want the software to configure the tests, taking those changes in the settings on the relay into account without me having to go into the relay or read the relay with the relay's, let's say, proprietary software and do the changes on the settings for the test myself. I can get RTMS to read the settings from the relay and to configure the test, taking those settings into consideration. So how are we going to do that? Well, the first thing that we need to do is we need to read the settings from the relay. Now, to read the settings from the relay, what I'm going to do now, I want to mention that I started from scratch with this relay, let's say the test sheet. I have started from scratch. I opened the PowerDB, and the PowerDB that I opened was PowerDB Lite. You can install this PowerDB simply by going to our website and download it from there, and there is no licensing fee or anything for the things that I have shown you so far. And for most of the things that I'm going to show you when it comes to importing settings and whatnot, none of this you have to get any license for or anything. You can simply download the software and do everything I'm going to tell you right now with the typical and with the software, with the light version of the software. And also, I wanted to point out that I am building the module in front of you. I am not doing this, with a pre-built or anything. I'm going to import the settings from scratch as if you were doing it and you had only the software at your disposal right there. So the first thing I'm going to do is I'm going to find this button here that if you scroll over it, it says, or if you hover over it, it says relay settings. So I'm going to enable the edit mode so that I can change the settings, and then I'm going to import the settings from the relay. Now I am connected, as you guys have surmised, to a 751A relay. I'm using accelerator here, and I'm going to use SEL serial. Now, something that you guys don't know is I am connected to this relay using Ethernet, which means that I can connect using serial without any interference from the communications on the relay part. If I were connected using serial, I would have to stop the connection here with accelerator, but I'm not doing that. I am connected using Ethernet so that I don't have any interference between the communication on the RTMS and the relay and the communication between accelerator and the relay. So I'm going to use SEL serial. I am connected using COM port 8. If you guys don't remember or don't know, well, you can always go to the device manager and find out what ports you have in this case. In my case, I have two SEL USB to serial, and I have a prolific USB to serial as well. I know that I am connected to that when using this COM8 right here, and I also know that that relay I am connected at 19200. So what I'm going to do is simply select the COM port, the baud rate that I have on that on the port on the relay, and read from the relay. Now the software is logging into the relay. This is going to take a minute or something. And what it's doing is it's reading the settings corresponding to the commands that you saw there on the screen. It's putting them in a intermediate file, and then it's going to bring them all into the software. Now, what it's telling me is, would you like to create new settings from the remaining settings? Because I don't have any settings right here. So I'm going to say yes. I want you to create settings from those that I don't have right now. And what the software did was it imported all of those settings into my software right here. Now I have this folder that was created by that process of importing the settings into the software that's called general. Now the name here, it's just because all of these settings that I have right here, the software couldn't find, let's say, a way to group them by protection function or some other general class or characteristic. But those settings that the relay was able to classify as for a different protection function, etc., the software did so, and it created different folders for elements like the 50, the 51, the 27, etc. And it can do that because those settings all start with the number of the function. So it simply groups them together. And the thing is that once the settings are here, you can change them to your advantage. You can change the name of the groups. I can enter a new folder name instead of general. I can call it something else. Element 51. I could call it, instead of element 51, I could call it 51. And things like that, and then the name will change automatically here on this list that we have right here. Now that we have the settings in here, we can do several things with them. One of the things we can do is we can edit the setting, and we can change the type of the setting. We can say, no, you're not a string, you're something else, you have this or that default value, etc. I'm gonna leave those let's say details off of this presentation. I'm gonna leave it for those who will actually be interested in creating their own types of settings and whatnot. But what I'm going to do now is I'm going to show you how I'm going to connect the settings values that I have right here with the settings of the tests that I have just performed. So a few things that we need, I don't know if you guys remember this, but on the relay, we had, for example, elements 1 and 2 on the instantaneous, and the names of those variables or those settings were 50p1p or 50 phase element 1 pickup, and 50p1d, same thing, delay, and 50p2p, well, element 2 pickup, element 2 delay. So we know that we have these names here, and the same thing with the time over current elements, 51p1p, p1c, etc. Now, what I'm going to do is the 51p1p is this one that I have right here. 51p1c is the curve, 51p1td is the time dial, etc. So what I'm going to do is I'm going to bring this element into my scripts. Now, in the scripts, where do I have them? I don't know if you guys remember, but we had a group of tests called overcurrent, and inside that group there was the overcurrent timing. And what I'm going to do is I'm going to bring those settings into the overcurrent timing, right? All right. So what I did is I brought those settings into the script that corresponds with the overcurrent time. So now here I have the 51p1p, which is the pickup, the curve, and the time dial of the element 51. And these variables correspond with the value that those settings have on the relay. I have just read them from the relay myself. So I'm going to do the same thing with the element 50. Now, because remember, we have both an element 51 and two element 50s. So I'm going to bring the 50p1p, okay, and I'm going to bring it to the same place. the 50p1d, which is the delay, and the 50p2p, okay, and the 50p2d, which is the time dial, or the time delay in this case. Okay, so now I have them all right here, but this is only the relay side. Okay, these are the variables on the relay. Now I need the equivalent variables, but in the software. So what I'm gonna do is I'm gonna go to my overcurrent timing screen, and I'm going to bring those variables to my script. Okay, so this is the pickup, this is the time dial, and this is the curve. Again, pickup, time delay, pickup, and time delay. Okay, so now I can go back to the module, to the script, and now I have the variables coming from the relay and the variables coming from the test. Okay, all I have to do now is pair them. So the pickup for element 1, I know it's this one, S1 51p. The pickup, the curve, I'm gonna leave the curve there for now. The time delay or time dial, in this case for the 51. Okay, I'm gonna delete it and delete it. 50p1p. This is instantaneous pickup. 50p1d. $50p2d. Now, this looks like a lot of work, but believe me, this gives you absolute control over the behavior of the software. And with this, you can create the most incredible automations in your test plans. So now I have already mapped, let's say, my pickups, my time dial, pickup, time delay, pickup, and time delay of my 51s and my 50s. I have left the curve for later because the curve has a different form coming from the relay than the form that I have for the curve on the software. So we will have to do some matching there. Fortunately for you, we already have the scripts to do that, that kind of matching. So when I do this, what's gonna happen is that in the test, whenever I have a change on the relay, which I'm gonna do right now, let's say my 51 time over current pickup, I don't want it to be 4, I want it to be 6. And my on my phase over current, I don't want to go 15, I want to go, let's say 19, and instead of 27, I want to go 30. Okay, I'm going to send those settings to the relay. This could happen in the field. You have 2 relays that are the same 751A, but they have different settings. Okay, so you have one on feeder number 7, the other one is on feeder number 8. They're one next to the other, and all you have to do is read the settings from the relay with our software, and the tests will be configured for you. Now, I have changed the settings. Before those changes can come into my test sheets, I have to go back and read the settings from the relay again. Okay, I am going to do the same. I'm going to read the settings from the relay right here, just doing it again. Okay, and you will see how these numbers will change And not only these numbers will change, but the settings will be mapped into the test by the software. Now, again, I'm just logging into the relay. Would you like? Yeah, see, now I have 19 and 30. And when I go to the test, now my pickup is 6, my instantaneous is 19, my second instantaneous is 30. And not just that, I can go ahead and redo the test, okay? I can redo the test, 67.5, okay, I'm not gonna inject 67.5, but I am gonna inject 60, why not? So what did I do that was so complicated? Nothing really. All I did was get the settings from the relay, read the settings from the relay, find the appropriate settings. Again, you don't have to map every single setting on the relay. You only have to map those settings that from the relay that you need for your testing. Now, I'm doing this with a Schweitzer relay, but there are many relays out there that will give you the settings either in a CSV file or in an XML file, or you can do, if you don't want to read directly from the relay, but you have the TXT file coming from the Schweitzer relay, you can do it here. You can do the XREO. You have to find a way to get the settings into the RTMS. Once you have the settings in the RTMS, all you have to do is map them, and you can automate your testing like that. This gives you extreme power, and the thing is yet that it's all available to you without having to pay any license for it. All you have to do after doing this is save the file, as I'm gonna do right now. I'm gonna give it a name. It's 2020 August 4th. It is a 751A, and I'm gonna say I created this module here in the webinar. Okay, you can reuse it. You can change the names and whatnot. You can test the same relay several times. Let's say you have to test the same relay every 2-3 years. You can reuse the same test sheet to test the same relay. Once you create this automation, you can apply it to as many relays as you want. Typically, the settings that matter don't change the name over time, so you can use it over the different generations of the same type of relay. So now the one thing that was missing is the fact that we did not map the curve. Why? Because the curve name on the relay is shown as, let's say, C1, okay? But when you look into the RTMS, the curve name is shown as something like this, C1-IEC standard inverse. So we need to create some kind of code that when it sees C1 on the relay, it matches that with C1-IEC standard inverse. I'm not gonna go over how to do that exactly, but it's a simple if the curve that comes from the relay equals C1, then make it C1 IEC standard inverse. Okay, and since we have all the choices for the different curves on that type of relay, and we know the choices that we have for the relay inside of RTMS, then we can create a simple matching code that we can apply on the script right here. And I can do that. Let's say I'm going to do it down below. So if you look here, all that I'm missing is giving this piece of code the exact name of the curve that comes from our relay, which is 51P1C. So I'm going to do that here is P1C. And that will tell my software that the curve that I'm going to use is the IEC standard inverse or whatever curve I have from there. Now, if you look here, this part of the this column that I have right here corresponds with the name of the curves as they come from the relay. And this side that I have right here corresponds with the name of the curves as they are in the RTMS. So this is, I would say, the only thing a little bit fancy that we had to do, but it's not that fancy. For those out there, and I believe that anyone can do this type of coding today, it's just if the curve equals a U1, then the actual curve that I'm going to use is U1 moderately inverse. Now, this code will work, and now I can go ahead and do the same thing. I could even change the curve, and instead of using a C1, let's say I use a C2, change it again. Okay. And I can read it again from the relay. One thing I could do is I could simply change this to C2, but I want you guys to, I could do this C2, but I want you guys to see the fact that I am actually reading it from the relay. So I'm going to do it again. Okay, yeah, now I have a C2 here, and not just that, now on my curve, you can see that it's a C2 curve, okay, C2, now the curve is different, but I can test it again, right? And again, these are real tests, I'm not simulating or anything. Now, what happened with this point here? What happened with this point here is that it was exactly on the edge. So instead, I'm going to use 4. Will 4 work? Yeah. And I'm going to run the point again. There. So now I have my whole test, okay? And I have it automated. No matter what changes happen on the relay with those elements that I have right there, I can always read the setting and I can run the test, and I don't have to worry about, oh, did I configure the test right? Did I configure the test wrong? Did I do something right? Did I do something wrong? I could even configure other types of elements following the same, let's say, procedure. My goal with presenting this in this way was to empower everyone, you know, to go ahead and do these things for different types of relays and for different types of settings, and to start experimenting with this very, very powerful tool that we have created and that we want to put in your hands. And because that's the whole idea here, is that everyone can create their own test modules and start, you know, experimenting and start, you know, increasing the flexibility of the types of tests that you guys are doing. Now, so far, we have been testing and we have been running different tests on the relay. Now, what I'm going to do right now is I'm going to go into the relay and I'm going to look into the events that have been saved into the relay. Okay. Now, I'm going to get the 16 samples. I like it a little bit better. Okay. And let's say now this last event, this last one is the number 3, the row number 3 that we tested. So I'm guessing this number 5 is gonna be number 2 here. Okay. So I'm going to get it from the relay. Okay. It's gonna be saved under all right. So I can go to okay, I believe it's right here. And okay, here it is. So this is the event that was just created on that on the relay. All right. Now that was let me get another one because that one's a bit short and I want to show you some other stuff. Let me run this number 2. Okay. Choo. All right. So I'm gonna get it. And I'm gonna do the same thing. There you go. This one is a bit better for instructional purposes. Now, this event that we have right here, what I did on the relay is I asked the relay to save those reports with a 3 cycle pre-fault, 64 cycles in length, but I started the event on the pickup of the 51 and on the pickup of the 50. So I didn't start it on the trip because if I start this one on the trip, then I only get a piece of the event. I started it on the pickup so that I could have the whole waveform or the whole test that I created or that I ran on the relay. Now I'm going to export the Comtrade into here. Now this is going to be web now. At webinar, I'm going to call it 51. And I'm going to use a tool in Rtms, which is the Comtrade playback tool. Now, with this tool, what I'm going to do is I'm going to import. No, this is not here. This Comtrade. Okay. Now I have a maximum RMS of 2,162 amps, which if I leave it there, the unit is gonna go crazy. So what I'm gonna do is I'm gonna go to the relay settings that are incorporated on the event, and I'm going to read the CT ratio, which is 120. You can see it here. And I'm gonna use that CT ratio over here, 120. Okay, and no. Now I'm gonna show you what the event looks like, and this is what I'm going to play back into the relay. Okay, now this is a tool that's used, I would say, in forensic analysis. It is also used in, and when I say forensic analysis, I'm maybe taking a name from the movies or from another domain in science or technology, but a lot of times you have a failure or a fault in the system, and you have to play back the events that resulted from that failure to figure out if the relays that were involved in the fault acted correctly. So you take the result. I guess I'm describing a process that would be familiar for many, but there is also other uses for this, which is doing end-to-end testing using this type of files. You can generate the faults with a more, I would say, realistic form than this one that I have right here, with a DC component, with harmonics, with other elements incorporated. What I did right here was I created a fault, played it into the relay, and took it from the relay and back into the realm of the RTMS. Now, a difference between this test that I'm going to do right now and the tests that I was running with the overcurrent test on the RTMS is that in here I have a small window of pre-fault. Okay, now this window of pre-fault is the 3 cycles that I told my relay during the configuration to save before the actual fault report was generated. And the thing is that when I'm using the overcurrent timing screen, there is no pre-fault, or I chose not to inject any pre-fault, and therefore there is no time between the moment of the injection and the actual amount of current that, or the actual injection of the full amount of current that I injected for that for that fault. Why do I say all that? Because that is going to change the behavior of the relay a little bit. So now what I can do is I can play this fault into the relay, but before doing that, I'm going to ask this timer configuration tool to give me a timer between the moment when I start the playback and binary input number 1. Binary input number 1, as you guys remember, we have been using it throughout the entire presentation, is connected to the relay's output. So what I'm essentially doing is I will be timing between the start of the Comtrade and the trip of the relay. I could, if I wanted to, use other things as my start. I could start on a binary input. I could perhaps use the pickup signal from the relay and trip between the pickup signal and the trip signal of the relay. I could start on a cursor. I could start on a trigger. For instance, I'm going to choose start and play, because that will allow us to see some really, I would say, interesting characteristics of using Comtrade playback to test relays. So when I do this, I hit play here. What's going to happen is the file is going to be saved into the unit, and then it's going to be reproduced. I'm going to have those 18 amps being played back into the relay. There was a trip, and now I'm going to be able to measure the time that that trip took, 625 milliseconds. Okay, now keep that in mind. I'm going to I don't know, make a note so that I don't forget. For those of you with good memory, no, this is not a good one. I'm just gonna make a note here, 625. Okay, so what I want to do now is I want to compare the time that I got from my previous test with the time that I got from the Comtrade playback. Okay, now my previous test was this one. Remember, it was row number 2. I got 557 milliseconds, and now I'm getting 625. Okay, so we can see that the difference is 625 minus 557. There's a difference of 68 milliseconds between one trip and the other, and we are essentially playing the same fault. Okay, because we are injecting the same 18 amps, and we are doing essentially the same thing one time and then the next. So what is the difference about? Well, the first thing is that if you remember the configuration of my timer, in the configuration of my timer, I said that I wanted to time from the moment where the playback begins. But when the playback begins, there is nothing. And there is nothing for how long? Well, I know that it should be 3 cycles. Now, can I, let's say, verify that? Yes, I can. I can set a cursor here. I can set a cursor right here. And I can see that these are, let me try and a little bit better with my zoom. These are about 50 milliseconds. Okay, I can see right here that there are 50 of the 68 milliseconds that I have left. So I have about 15, 16 milliseconds that I cannot account for. All right, so what do I do? Well, I have to go back to the relay and get the events again. Okay, so where is my event history? There it is. So I want to refresh it. And I have this one. I'm going to get it. And here it is. So are they the same exactly? What's this one? If you look at them, they look like exactly the same. And the oscillography itself is no different. They are essentially, they have the same oscillography. The relay started recording here. It took 3 cycles before it, recorded nothing because there was nothing, and recorded exactly what was being played back into the relay. But what is different now? why the one event gives me a trip time that is about 15 milliseconds different. And I want you to look at this. You have here, I have my pickup, my 51 pickup and my 51 trip. Okay, so between my 51 pickup, okay, which happens here, and my 51 trip inside the relay, there are 542 milliseconds. All right, but between the pickup, I'm sorry, between the trip inside the relay and the actual dying out of the current, there are 15 milliseconds. So there's a time between the emission, let's say, of the issuing of the trip command and the actual dying out of the current on the test set. Now, a part of that has to do with the fact that the test set doesn't stop the current immediately. It will stop the current as close to zero as possible. Okay, but that still doesn't account for the rest of that time. My let's say educated guess in this case has to do with the fact that the relay has an electromechanical relay on the output that has a bit of time to act, and when you put those two times together, then you get a difference in time that is, I would say, inevitable. It's one of the reasons why you never say that you have zero trip time. That happens, it's not particular to this relay, that happens to every relay that has an electromechanical output. If you have a fast output, you could reduce those times. And this is the type of thing that I would say you can investigate using Comtrade. Sometimes you're crazy looking for, oh, I have a few milliseconds that have nothing to do with this, and how do I account for them? And you have to realize that there are differences between the time that the commands are issued and the digital signals appear on the inside the relay, and then you have 4 milliseconds depending on the type of relay that you're talking about, of processing time, and then you have the test set, which doesn't behave also, you know, absolutely instantaneously. So when you put all those little bits of and pieces of time together, then you get this this difference. In my opinion, it's 4 seconds of processing, 8 milliseconds. I mean, 4 milliseconds of processing, 8 milliseconds of the mechanical trip, and 4 milliseconds for the current to die out on the relay. It's on the test set. That's my interpretation of this case right here. But now I want you to look at the original file. Right now we have this. Okay, let me close this notepad. Don't save. This is the original file, and I want you to now look at the new one. Now on the new one, what we are going to see is that the time between the actual initiation of the wave and the trip, the pickup, I'm sorry, the pickup signal is about 10 milliseconds. See, the wave starts being generated here, and then you have 10 milliseconds on the generation. Whereas on the other one, you have 8 milliseconds, right? So it's the behavior of the relay, even though the fault is apparently the same, varies a little bit between one moment and the next. And also there is the same thing that I was talking about on this side, where you have the difference between the trip and the actual extinction of the current here of 15 milliseconds. And not just that, you will also have a different time between the actual pickup and the extinction of the current in between both. In this case, it's 558 milliseconds. What I'm trying to get at here is that you have a powerful tool that allows you to take events from relays and find them and put them in a digital format, and then play them back to the same relay or to different relays to see the differences in behavior between the different relays. And you can play not only the analog signals, but you can also play the digital signals on the that are present on the event file as well. Remember that the SMRTs, they have a set. In the case of the SMRT that I have right here, I have 6 binary outputs, and you can assign these digital signals to those binary outputs, and the digital signals will, for instance, a signal that I know was activated was the 51P1T, and I also know that the 51P1P was activated. Let me see where it is. P1P, it's right here. So when we go back to the Comtrade tool, we can see them, and we can set and we can calculate the times between the pickup and the trip using our Comtrade tool. In this case, 542 milliseconds. And the thing is that you can play with 6 different binary outputs on the test set, which you would then, what you have to do is you have to connect these binary outputs to the binary inputs in the relay, and see how the changing in the binary outputs creates changes in the binary inputs. And then you can create things like block out, block signals, enablers. You can simulate communications and things like that. So you can use this to do the type of dynamic testing that is only possible when you have a signal that is very close to the actual behavior of the relay in real life, which is different than the static testing that we are mostly used to doing when we are doing maintenance and things like that. So the last thing that I wanted to get into, and this is because I had a request from someone who watched our previous webinar, and he wanted us to do or to show him how to import. Now, let me say how to import settings from a relay that had Modbus. So instead of using the SEL serial protocol that I showed you in the beginning, or using importing from text files, etc., he wanted us to show him how to import settings from a relay using Modbus Ethernet. So I'm going to do just that. I am going to, in this case, I'm going to create a new file. So I'm going to close this one. I am not going to use the Schweitzer anymore. Let's say yes. So let me open PowerDB again. Now remember, you can open PowerDB, then SMRT. I'm using Ethernet. Okay, I am connected to my unit. Okay, and in this one, what I want to do is the same thing. Relay settings. Okay, edit mode. import, export, and it's the same thing. Read from relay, Modbus, all right? And I am going to use Modbus Ethernet. Now, to do this, I am going to have to go to in the relay, and I'm going to have to find on the relay. Now, the relay that I have here that I am going to use Modbus Ethernet on is an F60 relay. So you have to go in the relay and find your Modbus address. Now, I am connected to that relay using the same Ethernet port. So here under settings, communications, Modbus protocol, you will find the Modbus slave address, 254 in this case, and the Modbus TCP port number, 502. So 254, I've already used it, 502. Okay, and we need the IP of this relay, which is 169.254.225. Okay, and now we can read the settings. But what's going to happen? What's going to happen is that the software is going to go and read the settings, but it doesn't have anything to attach those settings to. It can't put the settings here because there is no Modbus map created yet. Okay, so I'm gonna what I have to do is I have to create a the Modbus map for that relay first. Now I have created a small one for you. So it's here. So what you have to do is you have to be able to create your map. Now, to create the map, the Modbus map, you have to find the relays Modbus map. Now, the relays Modbus map, you can find it on the relays IP address. Let's say I'm going to connect a new, and I know that the relay IP address is 169.254. So I just find a browser 169.254.225, and this is I am connected in real time with this relay that I have behind me, and I find the Modbus memory map. So here I can find the settings that I want to read from the relay. Let's say, and just for the sake of an example, that I want to read the order code of that relay. Now, the order code is not just an idle number. It's very important when you're doing the automation of the relay setting and the relay tests, because this order code tells you what module is connected where, and it helps you figure out if you have current, how many current channels you have, what's the meaning on the inside the relay of source 1, source 2, and things like that. Where do you connect your outputs? How many outputs do you have? How many inputs do you have, etc. So reading the order code is a very important part of automating the testing of a multi-link relay. So the first thing I want to do is on the order code, we need to find the Modbus address. In this case, is 0040. Okay, and we need to find the format, the data format of that order code. Okay, it's F204. Now, the Modbus address is something that we are going to have to use. Okay, in this case, I already created it. I already created this. Okay, but the Modbus address is something that we are going to have to use when we create those settings in RTMS. So in order to create the settings here, remember edit mode, I need to enable the edit mode, and I am going to create a new setting. I'm going to give it a name. Let's say it's the order code, so it's going to be general. The setting name, order code, comment, order code of the relay. So I know it is a string, okay? And now I have to show Modbus. Now it's asking me here for the address. Now, the one particularity that you have to know about the address is that it's asking you for the address in decimal. So if you know something about Modbus, you know that this 0040 is actually not the decimal number. It's actually an hexadecimal number. So what I'm going to do is I'm going to convert that. I'm going to use, I could, do it myself, but I'm just too lazy. So I'm going to say, hey, please do it for me. Convert this into hex for me. And of course, that's 16 times 4, that's 64. So I am going to use that 64 in here, okay? There's no scaling in this case. It's a string. There's no increment. And now the one thing I need to know is the number of registers. How do I know the number of registers? Remember when I told you to pay attention to the format of the Modbus element that we were importing. It's F204, right? So now, and believe me, this is the way to do it. You go in the relay manual, you find the F204, and you find the number of registers that the F204 type will have, right there. So it's telling me that it's an 80 character ASCII text. I know that a 20 character has 10 registers, so 4 times more is 40. So I'm going to use 40 registers here. And it's a Modbus type string, okay? Because that's what I'm importing right there. So now I can use this to import that element into my test sheet. I can use that same procedure. If you see, it was very fast. I just read the order code of the relay into my test sheet. Remember, you don't have to read every single element of the map. All you need to read into your test modules are those elements that are relevant to the tests that you want to perform with that test module. So you don't have to read every single element. You don't have to go over the thousands of elements that you have in the map of the relay. But you can read a few of the, let's say, over current, over voltage, distance element, frequency, etc., and you can convert them into a usable format that you can then assign to the different tests that you have on the relay. Now, summarizing what we have done, I read the order code of one a relay. Now, from this one that I was creating here for the purposes of the presentation, I can read several, not just the order code. In this case, I am reading no, just 54. Several elements from the relay. It's the same relay, so I'm gonna get the same order code, and I'm gonna get a CT primary and CT secondary. And what I have here are just different types of Modbus addresses and number of registers, Modbus types, etc. For instance, this one It's the address is different, 17537. It's just one registry. It's an enumeration. It can be either 1 or 5. The default is 1. Actually, on the relay, it can be 0 or 1. We're just changing it here to 105 or 5 to make it easier to use in the scripts. And I have this one, for example, which is just a numeric type, an integer, which tells you the primary value of the CT number 2 on the relay. These are elements that are important for the configuration of tests, etc. on the relay. You can build a map as long as you want it. It just grows, and you can then group the settings under different types of on the different classes, on the different groups, etc. Another type of settings that you can read is, let me close this one. Who are you? Oh, this is the. Okay. Another type of setting, there's the. Another type of setting that you can read using Rtms is when you have the settings in a text file. Sometimes, instead of having the relay with you, what you have is a settings file that somebody sent you. So what you can do is you can export those settings to a TXT file, and I have one here that I just did. So you can read them, and you can read all the settings into, and you get the same type of grouping that you had when reading the settings from this way. You can exchange, import, and create test modules and settings for someone or for yourself without having to actually have the relay in your hand. That is very powerful. Also, if you already have the settings in Rtms, you can go and export those settings into an Rtms type of CSV, which can then import into Rtms. You can send them again to somebody to read the settings in case they don't have the settings. Of course, you could always say, okay, I'm going to send him the module, but sometimes what you have is a CSV file with the settings. You can simply read them into the Rtms and have them in here. I have made a lot of emphasis in this thing about reading the settings and being able to read the settings from the relays, because it is the kind of thing that it's something that you will not get a lot of easily accessible information about it. It is something that it's very powerful for you. It's very powerful because it allows you to create value with this tool. It allows you to go beyond the simple, I'm going to use this tool to test and that's it. It allows you to use the tool to create value for yourself, for your company, for the people around you, to grow, to make the tool grow and have more value than just a simple, hammer that you have in your hand and for which everything that you have out there, and so that And I'm trying to show you that you're not confined by whatever RTMS has in store for you when it comes to testing. You can, using the same type of programming that I showed you, you can change the behavior of RTMS to make it to make your tests personalized, not just when it comes to the setting, but also to the behavior of RTMS itself. And we want you, I guess we want to encourage you to do that and to explore that to make the tool yours. I guess, Mike, with this, I have finished my presentation. I don't know.
Sounds good.
Yep.
So at this point, we've wrapped up the presentation portion, so we're all set.
Sorry, Mike.
No worries. We'll jump on into there, and we'll take a little bit of time to answer as many questions as we can. If you have any questions, please submit them now into the Q&A box on the right side of your screen. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or quote on any Megger products. A copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. You can also view video recordings of previous webinars as well as register for our upcoming webinars on our website at us.megger.com/webinars and register for our next webinar, how to perform instrument transformer testing with the Megger MRCT instrument. All right, let's jump into your questions. The first one I have, I'm going to be directed towards Mr. David Beard. David, when you import settings, does the function only import the settings of the active group?
Okay, you can hear me, Mr. Mike, correct?
Yep.
Correct. Awesome. Hey, yes, that is a true statement. Now, when you, so in RTMS, whenever we read the settings, we're reading the settings of the active group that's enabled in the relay at that point in time. Let's say, for example, you have active group number 1, and then you might have, that's your normal everyday settings that you're going to use, and then you might have what I've seen is storm settings, so if you might have a storm coming in the area or some weather coming in and you want to switch those to an alternative setting group, there is you can test both groups. The thing is that when you load, when you read the settings from the relay, it's going to tell you whatever that active group is at that point in time. That will technically be your relay settings that you will test on. If you need to change to an alternate group or group 2 or 1 through 6, however many groups the actual relay has, then each group can be classified as a relay. So each, you would read group 1, you would test your relay, and then you would save that information and result and template off. And then your second group would be it's the same relay, it's just a second group because all the settings are still be available to you in that second group, but also allow you to test it, but you just have to classify it as a group 2 of the same relay and so forth until you complete all the groups that you need tested. So yes, you can do that. We do one group at a time. You would have to go into the group, into the relay and make the groups active on the other groups that actually have settings in them that you would like to test. Okay, that's it.
All right, thanks, David. Sugosh Kuber will be answering our next question. Sugosh, I see that there are 3 options provided in RTMS to test impedance relays. Could you advise on what method to choose when?
Yeah, so the 3 options that are provided, they are called the EZZ method, COF method, and third one is the undefined characteristic method. So the EZZ option, it provides more of a manual approach to perform basic impedance relay testing. The second method, which is the COF, it's nothing but the click on to fault approach. This particular method, I would say, provides the most flexibility and complete test capability. The reason I say that is that you have the options to choose either a generic impedance characteristic, or you can choose a specific relay type model from list of manufacturers. Also, another thing with this method is that user has the option to use multiple binary inputs on the test set to monitor multiple relay output contacts to test, different zones at the same time. So if you need to test a relay with unknown or its undefined characteristic, then you could use a third method, which is the undefined characteristic method.
All right, thank you. David, back over to you. Once tests are created, can we save off these tests into a template to be used later on?
Yes, you can. So when you create a test, so every time, like Abel was showing you, you were doing the time over current test. So whenever he created that test and went into that feature in that module, he will run that test, put in his settings, or if he's reading the settings from the relay, as he was showing where he was scripting the settings to mask the buttons and features inside of the timing screen. When he was doing that, he was actually creating a test. So once you get done with building that test and massaging it to how you need it to look, then whenever you run that test and you get a result, don't stop there. You can always take that test template and save it, because you've already done the work once. Don't go back and redo that work. And you can definitely resave those templates. You can save them off as a template. You can save off the results as a PDB XML file. You can save them as PDF file. And then whenever you do save as a template, it does allow you to come back and use those templates for other, say you have the same relay at a different location, very similar relay settings. This will allow you to utilize that same template. And even if it isn't the same settings, if you're scripting your settings values over to your template, then it will accommodate whatever the different settings are. You're still going to have the same test, right? So if you had like a feeder relay, you would still have feeder relay tests. The settings will be different, but you can still have those tests in the template. Save it also off as a template and give it to everyone else in your group, so you don't have to recreate the wheel again every time. You can just say rerun that test template. Now, another thing I will mention here too is when creating the templates, you can actually utilize the simulation mode. Before you connect to the relay test set, you can use the simulation mode, create your template, script everything that you need to put over from your settings tab, or from your settings tab over into your test template, and then it allows you to run the test to make sure your calculations and your values are correct, and then you can run it on a relay, or you can pass it to people that are out in the field, to other technicians to do in the field. So it kind of gives you a little bit of a leadway where you don't necessarily have to create it on the fly while you're sitting in front of the relay. You can also do some pre-work. You do some setup and then create those templates ahead of time. So there's a lot of good features in template creation. Okay.
All right. Thanks, David. Sudosh, could you please explain how to perform time synchronized testing using Comtrade feature in the RTMS?
Yeah, sure. So when you're talking about the time synchronized testing, we would be using something like a reference time signal, even from a GPS clock, something like a RxB signal. So when you would have to perform this time sync testing from the Comtrade, I'll let Abel pull up an example Comtrade file just to show. So once you have this Comtrade file here, what you could do is you could go back to the nameplate there of the file and then click on Start Now. So it provides you multiple options as to when you could start this test from the Comtrade screen. So let us say you're performing this synchronized test because you have multi-ended systems that are set up. So you could start the test on IRIC-B, right, on multiple ends. And once you click on Start IRIC-B, and when the test is actually run, once the play button is pressed, the user would get another window that will show the current IRIG-B time that is being read from actual GPS clock that is connected to the SMRT test equipment. And based on that actual IRIG-B time that is obtained, now the user has a choice. User could either enter that future time manually, or it could choose multiple options that are available to run the test. It can be a particular time plus 1 minute or 5 minutes. So in this case, of course, we are not right now connected to a clock, but in real, when you're connected to an actual clock signal, you should be able to run the test from the Comtrade screen.
Okay.
All right.
Yeah, I'm not connected to an IRIG clock right now, so
Yeah.
that's why I canceled the.
Yeah. Thanks, Abel.
No problem.
All right. While you're here, Abel, can the Comtrade system be used to play back voltage recordings to test the operation of a synchronizer?
Well, you could, but the problem is we don't have a sequence of Comtrades that you can test. We do, however, have a synchronizer tool that allows you to test synchronizers. You can test the synchronization feature using other tools in the RTMS, or you can test a synchronizer itself using this tool here. Now, this was part of the original idea of this presentation, was to talk about the synchronizer as a feature of RTMS. Unfortunately, the hour and a half of the presentation came too soon, but yes, there is a possibility of testing the synchronizer, a synchronizer using the synchronizer tool that we have right here. I'm going to run just quickly over it. You have the two systems. For those who know the workings of function of synchronizers, you know that you have two systems that you have to synchronize to, and you have differences in magnitude of the voltage, frequency of the voltage systems on both sides, and the phase of the voltage systems on both ends that you have to take into consideration. And in order to synchronize both systems, both the magnitude, the frequency, and the phase have to be within a certain differences that can't be bigger than those, right? So you configure that, and then you have different ways or different things that you can test with the synchronizer. You can ask the software to create the dynamic points for you. If you look at this screen here, you have a DV, or difference in voltage between the voltage on one side and the voltage on the other, and difference in frequency between the same thing, the voltage on one side and the voltage on the other. And you have different ways of attacking, let's say, these tests in the plane right here. If you attack vertically, you would be having a difference in frequency that's going to be constant. If you attack horizontally, you are going to have a difference in voltage that's going to be constant. And if you do so at an angle, then you're going to have the fact that the differences in frequency and voltage are changing as the test, moves from the outside of the characteristic to the inside of the characteristic. I would say, since we don't have all the time to explain it right here, but yes, there is a feature that helps you test not just the synchronization, but a synchronizer itself in RTMS. Okay.
All right, thank you, Abel. And speaking of synchronizer modules in RTMS, what applications does that apply to? The auto synchronizer, such as the 25A, or the generic sync check only?
Well, if you're doing a generic sync check, I would do that. Not over there. You can do the generic sync check, I guess, on the frequency. You could do, no, this is the frequency tool. The generic sync check, you could do it there, I guess, with the 25, but the synchronizer is more for a full-fledged synchronization tool, or a synchronizer. Okay. If you're doing the sync check, I would do the sync check with the regular testing. You can even do it using the sequencer. Remember that we have a very powerful sequencer tool that you can use to create different states, and especially since you have 4 voltages, you can connect 3 voltages to one side of the relay, the 4th voltage to the VS, and create the different states right here. And you can do it also, another way to do it, and I would say it's more, similar to real life, would be doing it using ramping, in particular, given the possibility of having multiple ramps, and given the fact that you can ramp when you're using advanced ramp, you can ramp more than one magnitude at the same time. You can, at the same time that you increase the voltage, you can decrease the frequency. You can change the frequency going from different, let's say, starting on different places. You can leave 3 channels with the frequency fixed and change the frequency on the other channel, and you can change everything. You can change the voltage, the frequency, and the phase. So if I were going to do a simple sync check, I would do it from here. And if I'm testing a synchronizer, you know, with the characteristic and whatnot, I would do it with using this one, the synchronizer tool. Okay. If whoever asked the question needs help with this feature, either of us is more than willing to help them, you know, figure out the particular test that they have to do. Okay.
All right. Thanks, Abel. I guess it looks like we are out of questions. If you think of anything else, please feel free to follow up with any of our presenter or our panelists. A copy of the presentation, certificate of attendance, and a link to the video recording of the webinar will be emailed to everyone in about 2 business days. I'd like to thank you all for attending. If you could, please remember to answer our survey. That survey will include a field for you to request a quote or a demo if you're interested. Once again, I'd like to thank you all for attending, and I hope you all have a great week.